Welcome to Module 6, Airflow, Pressure, and Air Distribution. In this lesson, we are going to slow down and look at what the BAS is really measuring when it shows airflow, duct static pressure, filter pressure, or room pressure. Air does not move because a screen says it should move. Air moves because the fan creates a pressure difference, and the duct system, filters, coils, dampers, and rooms all react to that pressure. Here is the field mindset for this module. Before changing a set point, verify the measurement. Where is the sensor installed? What is the high side connected to? What is the low side connected to? Is the tube clean, dry, and referenced correctly? A good BAS professional does not just trust the number. They understand how that number was created. By the end of this module, learners should be able to connect airflow, velocity, duct area, pressure, density, and sensor installation into one practical troubleshooting method. This is not about memorizing definitions. It is about making better decisions when a VAV box reports low airflow, a filter differential pressure alarm appears, or a building pressure complaint reaches the operations team. Think like a field engineer. If the airflow value looks wrong, ask whether the duct size is correct, whether the velocity signal is valid, whether the units were mapped properly, and whether the sensor is installed where the air profile is stable. If the pressure value looks wrong, ask where the reference is. The goal is to build confidence in the data before using that data to change the system. This roadmap follows the same order we use in the field. First, we start with the basic physics, mass conservation, and the relationship between airflow, velocity, and area. Then we separate the different types of pressure: static, velocity, total, gauge, differential, and reference pressure. After that, we look at pressure loss, air density, and measurement methods. Then we apply the ideas. We look at filter pressure. We compare duct pressure with building pressure. We work through examples. Then we close with a field scenario and an assignment. The key theme is repeated throughout the module. Verify what the pressure or airflow sensor is actually measuring before adjusting the control sequence. This diagram gives us the complete air distribution story. The air handling unit creates the pressure and airflow. The supply duct moves air to the branches. The VAV boxes regulate how much air reaches each zone. The diffusers distribute the air into the room. Then the return path completes the circuit back to the air handling unit. Notice that every value on this screen depends on location. A duct static sensor near the fan does not tell the same story as a sensor near the end of the duct. A VAV airflow sensor measures a local condition at the terminal. A return air path may include sealing plenums, leakage, doors, relief air, and exhaust interaction. So when we troubleshoot, we do not look at one number alone. We ask where the number came from and what part of the system it represents. Conservation of mass is one of the most useful reasonableness checks in air systems. Under steady conditions, the mass of air entering a system has to equal the mass of air leaving after we account for leakage, exhaust, outdoor air, relief air, and measurement uncertainty. Here is a real BAS example. Suppose the main AHU airflow says 18,000 CFM, but the total of all VAV boxes says 27,000 CFM. That does not automatically mean the fan is failing. It means the data set does not balance. Maybe some terminal units are using the wrong K-factor. Maybe the AHU airflow station is dirty. Maybe some points are in liters per second but displayed as CFFM. The professional response is to investigate the evidence before changing the fan speed or pressure set point. The formula Q equals V times A is simple, but field application requires judgment. Q is airflow, V is average velocity, A is duct area. If the duct is 24 inches by 18 inches, the area is 3 square feet. If the average velocity is 1,200 feet per minute, the airflow is 3,600 CFM. The dangerous word is average. Air velocity is not perfectly uniform across a duct. After an elbow, transition damper, fan discharge, or poorly located sensor, the air profile can be very uneven. One velocity reading can be misleading. That is why proper traverse locations, straight duct requirements, airflow station installation, and balancing reports matter. The calculation is useful only when the velocity measurement represents the duct. Static pressure, velocity pressure, and total pressure are related, but they answer different questions. Static pressure is the pressure available to overcome system resistance. In duct static control, this is usually the pressure the BAS is trying to regulate. Velocity pressure is the energy of moving air. It helps us estimate air velocity. Total pressure is static pressure plus velocity pressure. In the field, the most important point is this. A transmitter does not magically know which pressure you wanted. It reports what the tubing, pickup, orientation, and reference connection deliver to it. If a pickup faces the wrong direction, if tubing is reversed, or if the sensor is mounted in a turbulent area, the number may look precise but still be wrong. Most BAS pressure readings are differential measurements. That means there is a high side and a low side. A filter pressure transmitter compares upstream pressure to downstream pressure. A room pressure transmitter compares the room to a corridor or reference area. A duct static transmitter compares duct pressure to a reference, often mechanical room, or ambient pressure. This is where many problems start. If the reference tube is blocked, leaking, wet, kinked, disconnected, or exposed to wind, the transmitter may report a false value. The transmitter can be calibrated and still produce a bad BAS value because the reference condition is wrong. Before changing pressure control logic, always verify the high side, the low side, tubing condition, and reference location. The fan creates pressure, but the duct system consumes that pressure. Long duct runs, high velocities, elbows, transitions, branch fittings, dampers, filters, coils, diffusers, and terminal units all create resistance. When resistance changes, the operating point of the system changes. A dirty filter, blocked coil, closed smoke damper, failed VAV damper, or crushed duct can all increase pressure loss. Also remember that many pressure losses increase roughly with the square of airflow. That means a modest increase in flow can require a much larger increase in pressure. This is why simply raising duct static pressure can waste energy and still fail to solve the root problem. Air density matters because air is not always standard air. Density changes with temperature, altitude, barometric pressure, humidity, and actual operating conditions. Many field equations assume standard air because it makes the math easier. That is fine for many estimates, but we need to know when the approximation may be weak. At high altitude, for example, the same volumetric airflow can carry less mass. That affects heat transfer calculations and sometimes fan performance interpretation. If you are comparing measured airflow, calculated load, fan pressure, and energy use, make sure you understand whether the values are based on standard conditions or actual conditions. BAS professional does not need to overcomplicate every calculation, but they must know the assumptions. There is no single perfect airflow measurement method. A pitot traverse can be accurate when performed correctly, but it requires access, straight duct, multiple points, and good technique. Airflow stations can provide continuous values, but they depend on installation and cleanliness. Fan inlet or piezometer methods depend on manufacturer relationships. VAV terminal sensors depend on calibration factors, tubing, and minimum velocity. The takeaway is simple. A digital value is not automatically a true value. When a number drives alarms, resets, balancing decisions, or energy calculations, identify the measurement method and its limitations. Trend the value, compare it to field measurements when possible, and verify the units before making control changes. Filter differential pressure is a good example of why context matters. A high filter pressure drop may indicate dirty filters, but it can also happen when the fan is running at unusually high airflow. A low filter pressure drop may indicate clean filters, but it can also indicate low airflow, filter bypass, missing filters, failed tubing, or a transmitter problem. The best practice is to trend filter differential pressure together with airflow, fan speed, and operating mode. For example, do not make a filter replacement decision based only on a pressure reading taken during test mode with the fan at 100%. The pressure value is meaningful only when the operating condition is understood. Duct pressure and building pressure are different problems. Duct static pressure helps distribute air through the supply duct system. Building pressure describes how the building relates to outdoors or how one room relates to another room. Building pressure depends on outdoor air, return air, exhaust, relief, transfer air, leakage, wind, and stack effect. This is a common mistake in the field. A building feels negative, doors are hard to open, or air is pulling in through entrances, and someone raises supply duct static pressure. That may increase fan energy and noise, but it may not fix the pressure relationship. To solve building pressure, you need airflow balance and a stable reference, not just more duct. These worked examples are reasonableness checks. They help us decide whether the BAS data tells a believable story. A 24 by 18-inch duct has an area of 3 square feet. At 1,200 feet per minute, that is about 3,600 CFM. With velocity pressure, we can estimate velocity, but density correction may apply. With filter alarms, we must review airflow and operating mode. Do not treat these calculations as paperwork. Use them as professional questions. Does the result match the equipment size? Does the flow match the balancing report? Does the pressure match the sensor range? Are the units correct? The math is valuable because it forces the data to prove itself. This field scenario is exactly the kind of situation that creates wasted energy. Several VAV boxes reported low airflow, so operators raised the duct static pressure set point. The fan worked harder, energy increased, and the alarms remained. That tells us the action did not match the root cause. The investigation found an integration error. The airflow units were mapped incorrectly. The BAS was comparing the wrong value to the expected airflow. This is why professional troubleshooting begins with evidence quality: units, scaling, sensor range, K-factor, point mapping, and measurement method. Pressure changes should follow verified diagnosis, not alarm frustration. To complete this module, apply the checklist to one AHU or VAV system. Sketch the airflow path, identify the fan, supply duct, branches, terminals, diffusers, return path, and pressure references. Then identify every airflow and pressure sensor that affects control, alarms, or reporting. Before recommending a sequence change, verify the basics: duct dimensions, sensor range, high and low tubing, reference pressure, units, density assumptions, and filter differential pressure with airflow context. The next module builds directly on this foundation. Once we understand airflow and pressure, we can properly evaluate fan operating points, duct systems, static pressure reset, and VAV behavior.